Welcome, class. Today we're diving into the absolute blueprint of flight with a bright, energetic, and comprehensive look at the four forces that keep us airborne. I'm literally so excited to guide you through this masterclass. Whether you're a student pilot just starting out, or you're brushing up for your instructor check ride, this explainer is designed to be your ultimate study guide. We're going to cover everything you need to know about how our aircraft actually interact with the air, breaking down all that complex physics into clear, actionable knowledge. So go ahead and grab your notebooks, get your pens ready, and let's get ready to fly. We really have a packed syllabus today, so we'll move quickly. We're going to systematically cover the basics of flight and lift, then tackle drag and wake turbulence. From there, we'll dive into load factors and the ever-important VG diagram, pull ourselves forward with thrust and propeller design, and finally, we'll conquer those sneaky left-turning tendencies. All right, let's jump right into Section 1, Basics of Flight and Lift. Okay, look at the perfect harmony going on here. You've got your four basic forces. Lift is pushing us up, weight is pulling us down, thrust is pulling us forward, and drag is holding us back. Now, huge note-taking alert right off the bat. In steady, unaccelerated flight, lift perfectly equals weight, and thrust perfectly equals drag. I cannot stress that enough. It is the fundamental balance of flight. When we climb, lift temporarily exceeds weight to create that upward force. And when we descend, well, lift is less than weight, which gives us a downward force. It sounds simple, right? But it's profoundly important for everything else we'll discuss today. Before we go any further, we absolutely have to master our terminology, especially when we're talking about our wing, or airfoil. So the wing has a leading edge at the very front, a trailing edge at the back, and an imaginary straight line connecting the two. We call that the chord line. Now get your pens ready again because students constantly mix these two up. Angle of attack is the dynamic angle between the oncoming relative wind and that chord line. You, the pilot, completely control this in the cockpit. The angle of incidence, on the other hand, is a fixed, built-in angle between the chord line and the longitudinal axis of the airplane. The engineers at the factory gave you that one, and you literally cannot change it in flight. So, the real question is, how does the wing actually create lift? Well, it's a brilliant tag team effort by two scientific heavyweights. First up, we have Bernoulli's principle. This tells us that as fluid velocity increases, its pressure decreases. So the air speeds up over the curved upper camber of the wing, and that creates a low-pressure void that essentially sucks the wing upward. Second, we have Newton's third law. For every action, there's an equal and opposite reaction. The wing physically deflects air downward, that's your action, and the equal reaction pushes the wing up. That brings us right to the lift formula. Notice how we as pilots control lift primarily by adjusting two things: our velocity, which is our airspeed, and our coefficient of lift, which is honestly just a fancy engineering term for our angle of attack. Remember, pitch for airspeed, power for altitude. What we're looking at here is the Magnus effect. Because of the airfoil's shape and its positive angle of attack, the air has to circulate rapidly over that top surface. The absolute highest velocity is right at the top of the airfoil, and that's exactly what creates that strong, low-pressure area we just talked about. The sharp trailing edge of the wing actually forces the rear stagnation point, which is where the airflow separates, to sit just aft of the wing. This effectively pulls that low pressure into a really powerful upward force. It's just fluid dynamics at its absolute finest. Moving right along to Section 2, drag and wake turbulence. So, drag comes in two main flavors, and you absolutely need to know both for your exams. First is parasite drag. This one actually increases as you fly faster. It's made up of form drag from the airplane's physical shape, skin friction from things like microscopic rivets, and interference drag right where surfaces meet, like where the wing's strut attaches to the fuselage. Think of parasite drag like diving into a pool from a high diving board. The faster you hit the fluid, the more resistance you feel. On the flip side, we have induced drag. This is simply a byproduct of generating lift. The high pressure under the wing desperately tries to escape to the low pressure on top, so it curls around the wingtips, creating downward acting vortices. And here is the total kicker, so write this down. Induced drag actually decreases as you fly faster. Why? Because the air spends way less time curling over the wingtip. All right, massive note-taking alert. Staring at this chart could literally save your life in an engine-out emergency. This is the total drag curve, which combines both parasite and induced drag. Do you see that lowest dip right there in the curve? That is your LD max, or your minimum drag point. Flying at this exact speed gives you the absolute most lift for the least amount of drag. If you fly any slower than this, getting behind the power curve as we call it, it requires massive amounts of engine power just to maintain your altitude, because that induced drag simply skyrockets. Now picture this. What happens when we fly super close to the runway? We enter what's called ground effect. When you fly within about 1 wingspan's height of the ground, the solid Earth actually physically blocks those wingtip vortices from forming fully. And because those vortices are blocked, your induced drag drops significantly. With way less induced drag holding you back and pulling your lift vector backwards, your wing suddenly needs less total lift to maintain altitude. Your whole wing basically becomes hyper-efficient. That's why it feels like you're floating on a magical cushion of air right before you touch down. But listen, those wingtip vortices aren't just some cool aerodynamics concept. They are a severe invisible hazard known as wake turbulence. The most dangerous wake turbulence is generated by aircraft that are heavy, clean, and slow. To avoid getting totally flipped by the wake of a preceding heavy jet, you have to memorize these steps to fly in the bowl. Always rotate for takeoff prior to their rotation point. When you're landing, fly your approach above their flight path and make sure you touch down completely past the point where their wheels hit the runway. Oh, and definitely beware of a light quartering tailwind. It can blow those invisible tornadoes right back onto your runway. Honestly, when in doubt, just wait the 2 to 3 minutes. Better safe than sorry. You might be wondering, how do designers fight induced drag? Well, they play with something called aspect ratio, which is just the wing's length divided by its chord width. A high aspect ratio wing, picture a really long, skinny glider wing, produces a tiny little wingtip vortex, which means very little induced drag. That's fantastic for climbing, but why don't Boeing 737s look like gliders? 3 main reasons. First, structural integrity. Just like extending a long tape measure, a long wing bends really easily and requires heavy structural reinforcement. Second is maneuverability. Long wings have a high moment of inertia, which absolutely kills your roll rate. And third, practicality. Try fitting retractable landing gear, massive fuel tanks, and taxiing a 200-foot wingspan into a standard airport gate. It's just not going to happen. Let's transition to Section 3, load factor and the VG diagram. All right, let's bank the airplane to turn. When we do that, our total lift factor tilts. This means the vertical component of lift, the specific part that's fighting gravity, actually decreases. If we do absolutely nothing, the nose is going to drop and will descend. So to maintain our altitude, we have to pull back on the yoke to increase our angle of attack and boost our total lift. But wait, that extra lift combined with the centrifugal force of the turn itself creates a really heavy resultant load felt right at the aircraft's center of gravity. At a steep 60-degree bank, you're pulling 2 Gs. That means you feel twice as heavy. And here's a crucial note for your checkride. As load factor increases, your stall speed increases dramatically. Huge note-taking alert right now. Draw a star next to this. This is the VG diagram, which plots your airspeed against G-loads. See that green box? That is your safe, normal operating envelope. For a normal category aircraft, your structural limits are positive 3.8 Gs and negative 1.52 Gs. If you fly outside this envelope by, say, throwing abrupt flight controls or flying way too fast into severe gusty turbulence, you cross that red line. Do that and you risk permanently bending the wings, which is structural damage, or frankly much worse, total structural failure. To protect us from accidentally breaking our own airplane, we have VA, or maneuvering speed. This is this magical speed where, if you pull the controls to the absolute limit, the wing will reach its critical angle of attack and stall before it can generate enough G-force to break the structure. The stall actually relieves the load. Now, here is a brilliant aerodynamic paradox you need to understand. A heavier aircraft actually has a higher maneuvering speed. Why on earth is that? Because a heavier aircraft already has to fly at a higher angle of attack just to maintain level flight. Since it's already flying so much closer to the critical stalling angle, any sudden gust or aggressive control input will push it over the edge into a safe stall much quicker than a lighter aircraft that's flying at a low angle of attack. Makes sense, right? Section 4. Let's talk about thrust and propeller design. Think about the basic physics of a spinning disc for a second. The outer tip of the propeller blade has to travel a massive circumference with every rotation, meaning it's slicing through the air at incredibly high speeds, sometimes over 380 knots. Meanwhile, the inner hub right near the engine is barely moving at all. If the propeller blade were perfectly flat, the super fast tip would produce massive thrust, and the slow root would produce almost nothing. That uneven force would literally rip the propeller apart from the structural loads. So how do engineers fix that? They twist the propeller. The inner portion has a very high angle of attack to compensate for its slow speed, while the fast-moving tip has a very shallow angle of attack. This brilliant design guarantees uniform thrust along the entire length of a blade. Now, if the propeller were screwing through a solid block of wood or butter, the distance it moves forward in one single rotation is its geometric pitch. But as we know, air is a fluid, so the prop slips backward a bit. The actual distance it pulls the plane forward through the air is its effective pitch. The difference between those two is called propeller slip. This is exactly why a climb-optimized plane like a Cessna S model uses a low pitch angle. It lets the engine spin fast and produce max power at slow airspeeds. Meanwhile, a cruise-optimized Cessna R model uses a high pitch to take massive, greedy bites of air for high-speed cruising. Finally, Section 5, the 4 left turning tendencies. First up on our list is P factor, also known as asymmetric thrust. When you're flying at a high angle of attack, like during a really slow, steep climb, the propeller disc is actually tilted back. Because the prop is spinning clockwise from your perspective, the right side descending blade is swinging down and forward directly into the relative wind. It takes a massive, high-angle bite of air. The ascending left blade is swinging away. That means the right side is producing significantly more thrust, effectively pushing the nose hard to the left. Number 2 is torque reaction. This brings us right back to our good friend Newton and his third law. The engine is applying massive force to spin that heavy metal propeller clockwise to the right. The equal and opposite reaction is the airframe desperately trying to twist itself to the left. In the air, this makes the plane want to roll left. On the ground during your takeoff roll, it presses the left main landing gear hard into the runway. That causes extra friction on the left tire, which tries to pivot the nose to the left. You absolutely must be stepping on that right rudder pedal to keep it straight. Third, we have the corkscrewing slipstream. That propeller doesn't just push air perfectly straight back, it throws it in a rapid, spiraling vortex that wraps entirely around the fuselage. As this tornado of air spirals backwards, it violently strikes the left side of your vertical stabilizer. That pushes the tail to the right, which in turn yaws your nose sharply to the left. This effect is most intense when you have really high power and slow forward airspeed, which, again, is exactly the situation you have on takeoff. And bringing it all home, we have gyroscopic precession. A spinning propeller acts exactly like a heavy gyroscope. Physics dictates that any force applied to a spinning disc is felt exactly 90 degrees ahead in the direction of rotation. It's just like leaning your body weight to steer a moving bicycle. In a tail dragger aircraft, when you force the tail up during the takeoff roll, you're essentially applying a pitch-down force on the top of the spinning prop. 90 degrees clockwise later, that force actually manifests and hits the right side of the prop arc, violently yawing the nose to the left. This is exactly why tailwheel flying requires such specialized training. So class, take a breath and look at all these complex forces constantly balancing on the edge of a knife. With a VG diagram, LD max, and these turning tendencies all perfectly mapped out in your notes now, how will you use this blueprint to make sharper, safer decisions the next time you strap into the cockpit? Think about that. Until next time, keep studying hard and fly safe.